This is the second video in our ongoing series regarding economies of scale. Today, we are going to take a closer look at cache memory. As we previously discussed, this is a specialized intermediate type of memory that sits strategically halfway between the microprocessor and the actual main memory. Its primary purpose is to significantly speed up the reading process, ensuring that the system operates much more efficiently than it would otherwise. We will see how this cache memory shares the principle of economies of scale. But first, let's take a closer look at the read operation. And to do this, let's assign a time to the read operation itself. Obviously, we are talking about the order of magnitude of microseconds of nanoseconds 10 to the power of -9. And we can give a realistic term. More or less, we can talk about 10 nanoseconds for every byte read. At this point, we can measure the speed by dividing the number 1 byte by 10 nanoseconds, and we get a speed of 100 megabytes per second, which is the speed at which we are using the channel. However, if we look closer at how the operation takes place, we see that the time is not entirely used for these 10 nanoseconds of reading, but a part of this time is dedicated to decoding the address, which is dead time. Decoding, which by the way lasts longer if the memory is larger, has a greater capacity. So let's assign a time to this decoding. Let's imagine assigning, for example, 2 nanoseconds to this time. So, in effect, the transfer time, if the whole process must last 10 nanoseconds, is only 8 nanoseconds. So we need to recalculate where we see that if there were no decoding, the maximum channel speed would be slightly higher, let's say significantly higher, because we would have 1 byte read in 8 nanoseconds, therefore a speed of 125 megabytes per second. So we are currently utilizing the channel for about, let's say, 4/5 of the time, which is roughly 80%. Now, the reason for this is primarily due to the significant amount of time that is unfortunately lost during the decoding process. And if we extend this discussion from a single byte to 1,000 bytes, to reading 1,000 bytes, and we use the same procedure, then we will still have 20% dead time, so 20% decoding and the actual transfer. We could call it payload by analogy with other situations of 80%. This is a graphical representation. You see, out of 10 little stars, 2 are occupied by the decoding time, which is not a real transfer, and then 8 instead by the actual transfer itself. The technique used by cache memory also has analogies with the DMA technique. It provides that the access to the 1,000 bytes occurs with the decoding of a single address. 1,000 bytes, with the important rule that they must be written contiguously, are read from the first to the last by giving only the starting address as additional information, the size, the number of bytes that must be read. So we have a slightly more complex decoding because it is a decoding, let's say, that doesn't concern just a single byte, but you also need to perform a kind of loop and state how many bytes are to be read. But after that, a uniform, continuous, uninterrupted read starts, which can reach, for example, 1,000 bytes in length. So in this case, the situation is a bit different because we, for example, have a transfer that requires 8,000 nanoseconds. So that would be 8 microseconds in this case. For 1,000 bytes. We know that the actual transfer takes 8 nanoseconds per byte. And the total amount of data read is 1,000 bytes. So we have 1,000 bytes divided by 8,100 nanoseconds. Why 8,100? Because I added to the 8,000 nanoseconds of the actual reading the time of 100 nanoseconds for the decoding of the, let's say, of this more complex address, of this multiple address, let's call it that. So we arrive at 8,100 nanoseconds. If we do the division, we realize that we get 123 megabytes per second, which is practically almost equal to the maximum speed of the channel. So this access allowed us to better exploit the channel speed. Just like the DMA as well. The DMA works more or less in the same way from this point of view, obviously. It allows for better utilization of the transmission channel, bringing it almost to its ideal speed. Obviously, there are some restrictions. We cannot make jumps. The data must be written contiguously, and from this we move to the principle of locality, which then has further important consequences. So in this situation, we have a decoding process that takes about 100 nanoseconds, which is 1.3% of the total time, and a transfer, therefore, a very high payload of 98.7%. At this point, let's say the graphical representation can be different. We have a peak, a time that is small in relation to the total time, and a quantity of data transferred that occupies almost entirely the time of the transfer, that is the transaction part. The dead time is almost negligible. Now let's come, as I told you, to economies of scale. If we take a moment to remember exactly how much time is needed to transfer a single byte of data, we can then go ahead and redo the entire calculation using this little formula right here. We can write it like this. The time is GI is given by the decoding time in the case of access width of the cache memory for the number of bytes downloaded multiplied by T1. T1 was the time that was sufficient to download a byte. So if we go and look at how much time is needed to download a byte on average at this point, we have T0 plus the number of bytes times T1 divided by the number of bytes downloaded. Therefore, T0 divided by the number of bytes plus T1. T1 is the time needed to load a byte. T0 divided by the number of bytes is precisely the amortization term, if you remember the previous video, related to dead time, in this case a transaction dead time. So we see that the law we are applying is identical to that of economies of scale. The principle is the same. Having a dead time and distributing it over a large quantity, in this case of data, to amortize the effect on the average read time. This same thing, I won't dwell on this much, also applies to file downloads. That is, if I have a short file, the dead time due to the transaction has a heavier impact, and therefore the speed is low. That's why, for example, we do compression inside a zip file of many files, so we can download a single large file instead of many small files. Because this approach allows me to significantly optimize the overall transfer speed. You see, the dead time inherent in each transaction will be distributed much less heavily over the, let's say, the transfer of a single long file rather than being spread across many small individual transactions. This makes the entire process far more efficient by minimizing the overhead impact. So this principle, we find it applied exactly the same way from economics to computer science. In this case, let's say to the hardware part of computer science. We'll see later. There are also other consequences, other similarities we can draw, perhaps a bit less simple, which also concern other situations, in particular Amdahl's law, which I will cover in a subsequent video. Goodbye.